yeah, I'm going to talk to you today about some joint work that I've been doing with erard-Helffer from Nantes. It's a project we've been doing for quite some time now, and we have several different results that I'm really pleased to be able to tell you about today. So my plan actually was going to be to have two parts. One part where I'll tell you some of the background to these Courant-sharp eigenvalues and motivate the question that we were interested in, and then a second part where I can share with you the results that we've found. And so in terms of where you can find these later, or you can find the references, for the background, the references are contained in papers 1 and 4 here, and then our results, the results that I present, also the figures that I'll show you, they are taken from these papers also. So yeah, I want to talk to you about Courant-sharp eigenvalues, but in particular for the Robin boundary, which you're probably already familiar with, but I'll just refresh it here so that I can fix all of my notations. So throughout the talk, I'm going to be working on Euclidean domains, and most of the time I'll assume they're bounded and connected and open with Lipschitz boundary. And then for me, H is going to be the Robin parameter. It's a real parameter, and I'm looking at the boundary, the Robin boundary condition here. So I have the eigenvalues of the Laplace operator with this condition, where I take the normal derivative of the function along the boundary plus H, the Robin parameter times U, equal to 0. And it's well known under these geometric constraints here that the spectrum of the Robin Laplacian is discrete, and so we can write the eigenvalues that I'll denote like this, lambda kh. And so one thing that will be important later is the relationship between the Robin eigenvalues here and the Dirichlet and Neumann eigenvalue problems. And of course we see here, if I take h equal to 0, then I'm looking essentially at the Neumann eigenvalue problem, whereas if I look at h tends to plus infinity, then it's the Dirichlet problem, because I'd need u to be 0 on the boundary to keep the condition. Or more explicitly, we can see it from the min-max characterization, where we have the infimum of supremum of the Rayleigh quotient here for the Robin condition, where when h is 0, we recover back exactly the Neumann condition, the Neumann characterization. And as h, if you can show formally that as h tends to plus infinity, here I'm looking in h10, the sublet space h10. So one thing which is important for the Robin eigenvalues, or at least for our discussion later, will be that they interpolate between the Neumann ones when h is 0 and the Dirichlet ones as h tends to plus infinity. That's in the case where h is positive. And we'll also be interested later in what happens when h is negative in terms of Courant sharpness, where we no longer have this nice Neumann and Dirichlet bracketing. Okay, so that's the, well, we're interested in the Robin eigenvalues, and we'll also be interested in the corresponding eigenfunctions. And in particular, we'll be interested in the places where the eigenfunctions vanish, which are called the nodal sets. So I'm going to take U an eigenfunction of the Laplacian, either with Dirichlet, Neumann, or Robin boundary condition. I'm going to try and keep the, I hope I've kept the color coding the whole way through. So anything that's red is for Dirichlet, green for Neumann, and blue for Robin. And so the nodal sets, it's the closure of the set of points where U vanishes inside our domain omega. And then the nodal domains, they're the complement of this set where U vanishes. So we see that the nodal set partitions omega into nodal domains, and we often call that the nodal partition. And we're going to be interested here in how many of these nodal domains are there. Of course, there's many other questions that are very interesting too, like how large is the nodal set, but we won't mention that today. We'll focus on the number of nodal domains. And so thinking about the number of nodal domains, we have, of course, in one dimension, the well-known result of Sturm, which tells us that for a bounded interval, the eigenfunction corresponding to the kth eigenvalue has exactly k nodal domains. And so this eigenfunction has exactly k minus 1 zeros. So that's for the one-dimensional case, but in higher dimensions, even for the square, it was shown by Stern that there is a whole sequence of eigenfunctions that have exactly 2 nodal domains. So we can't hope to have equality all the time in higher dimensions. And we have the celebrated result of Courant, which tells us that if I have the kth eigenvalue, then any eigenfunction in the corresponding eigenspace has at most k nodal domains. So we have an upper bound on the number of nodal domains. And for us today, the interesting eigenfunctions will be the ones that have exactly k nodal domains, so the ones that realize the maximal partition in terms of number of domains, and these are the ones that we'll call Courant-sharp. So if I take the kth eigenvalue and there is an eigenfunction with k nodal domains, then we'll call it Courant-sharp, and we'll also call the eigenvalue Courant-sharp. So what do we know about these? Well, when k is 1, Courant's theorem tells us there can be at most 1 nodal domain, and since the eigenfunction is not identically 0, there has to be exactly 1. So the first one is Courant-sharp. And then any higher eigenfunction, since we know they are orthogonal in L2, we know that any higher eigenfunction has to have at least 2 nodal domains. And so the second one will have to have exactly 2 by Courant's theorem. So the first 2 eigenvalues, they are always Courant-sharp. But then what happens for the higher ones? As I said already, for the square, there is a whole sequence of eigenfunctions with only 2 nodal domains. So we know that it's not always Courant-sharp. And so we'll be interested in for which k do we have a Courant-sharp eigenfunction and eigenvalue. And while I'm here, maybe just as a side remark that there is another motivation for studying the Courant-sharp eigenfunctions coming from spectral geometry, coming from the area of spectral minimal partitions, where you take your domain omega, you partition it into, let's take k subdomains, and on each one of those you consider the Dirichlet boundary condition. So you look on each one at lambda 1, the first Dirichlet eigenvalue, and you maximize among all domains in the partition. And then you minimize among all partitions, and that's the one which achieves this minimum is the partition that we call minimal, spectral minimal partition. And it was shown by Helffer, Hoffmann, Ostenhoff, and Terracini that the nodal partition corresponding to a Courant-sharp eigenfunction is one of these spectral minimal partitions. So there's quite a lot of motivation to study them. That was in the Dirichlet case, of course. Okay. So we're interested in how many there are, coming back to my main question, and there is the very classic result of Pleijel, which tells us that there are finitely many Courant-sharp Dirichlet eigenvalues. So it was first shown by Pleijel in 1956 for domains with sufficiently regular boundary in the plane, and then there's been later generalizations, also to Riemannian settings by Berhard and Meyer and others. Here we give it with finite measure, since that's what we need for a discrete spectrum in the Dirichlet case. But let me give you the more explicit version. So I'm going to let nu of uk omega denote the number of nodal domains of the eigenfunction uk omega, where uk omega corresponds to the eigenvalue lambda k. So we're talking all the time about Dirichlet here. And then explicitly what Pleijl's theorem tells us is that the lim sup of this nu of uk on k is bounded by a constant gamma n, and gamma n, it depends only on the dimension n. Bn here is the ball in Rn of radius 1. And so this constant, importantly, is always smaller than 1. So since the lim sup here is smaller than 1, we see that they have equality finitely many times in the sequence. So there are only finitely many Courant-sharp Dirichlet eigenvalues. And what I'd like to do actually is just give you a brief sketch of what the proof looks like of this result, because it will be important for the discussion which follows, and we'll also be able to see where some of the problems or some of the tricky parts come in when we think about the other boundary conditions, so the Neumann and the Robin. So what I'm going to do on the next few slides is talk about this Pleijel theorem for Dirichlet in 2 dimensions. And so I just wanted to point here that there is this gamma 2, approximately 0.69. That'll be important in a second. But to show you the proof of Pleijel, I need to just remind you 2 facts about Dirichlet eigenvalues. So we have, of course, the Weyl law, which tells us how the Dirichlet eigenvalues behave asymptotically as k tends to infinity, where the constant is only depending on the dimension and the volume. And there's also the Helffer-Persson inequality, which tells us that if I look at the first Dirichlet eigenvalue, then it's minimized by the ball of the same area as omega if I look in the collection of all domains of the same area. So for Plejel's result, what we would like to show is that there's finitely many Courant-sharp eigenvalues. So let's start off in 2 dimensions with lambda k Courant-sharp, UK Courant-sharp. So UK has exactly k nodal domains. Let's call those omega 1, omega k. Then on each of these nodal domains, the eigenvalue equation is satisfied, but we also have that the boundary condition is satisfied, the Dirichlet boundary condition, because we have that u vanishes on the boundary of each nodal domain. Since then we're interested in the nodal sets here, the boundary of omega is either the boundary of omega I is the boundary of omega or the boundary of the nodal set, so it should be vanishing here. So what we know is that on each of these nodal sets, u doesn't change sign and it's not identically 0. So in fact, the kth eigenvalue is going to have to be the first one on each of our omega i's. And then for the first Dirichlet eigenvalue, we can apply the Helffer-Persson inequality. So we take lambda k equal to the first on omega I, we replace omega I by a disk of the same area. And then I just rescale so that I obtain here the lambda 1 of the ball. And so once we have that, it gives us an inequality involving lambda k and the volume of omega I. And if we add up over all the nodal domains, we know that there's k of them. So now we have an inequality for k over lambda k. But we want to show that there's only finitely many of these eigenvalues. So if we let k tend to infinity, assuming that there's not finitely many, then we know how the right-hand side behaves here by the Weyl law. By the Weyl law, the right-hand side should tend to the volume divided by 4 pi, but we know that 4 pi is smaller than pi times lambda 1, because if we compute the ratio here, we get back our gamma 2, which was smaller than 1. And that gives us the contradiction. So Plejel's argument was like this by contradiction, and we have in fact that there's finitely many of the Courant-sharp eigenvalues in the Dirichlet case. So there's a couple of things that I'd like to say now about this. One of them is that you see where there'd be issues if you were thinking about the Neumann problem, because in the case of Neumann, we don't have the Helffer-Persson inequality. The ball is a maximizer for the first Neumann eigenvalue. So for the nodal domains in the Neumann case, which intersect the boundary non-trivially, they're going to have mixed boundary conditions, Dirichlet and Neumann. In the case of Robin, for H positive, we do have a Robin-Helffer-Persson inequality due to Bossel and Daners, and with less regularity, there are results of Pecor and Giacomini. So the ball is still the minimizer for the Robin case when H is positive, but then the problem is when you rescale here, you rescale also the Robin parameter, and it rescales in the case of 2 dimensions by the volume to the power of a half. And then the problem is that we don't know how small are the nodal domains. They could have very small volumes, so we might then arrive at a much smaller parameter than what we had to start with. So there's some issues in the cases of Neumann and Robin to try and apply this for the nodal domains which intersect the boundary. Another, just another remark to make is here, when we use the Faber-Kahn inequality, we do lose quite a bit, because we say that we'll replace every nodal domain by a disk, and maybe the domain that we start with won't have all nodal domains equal to disks. And this observation was already made by Josef Polterowicz in 2008. And the question that he gave a conjecture for what could be the best Pleijel constant. So we see already that this gamma, it won't be the best one, because we replaced every domain by a disk. And the conjecture of Josef Polterowicz is that among all regular bounded planar domains, the optimal constant should be 2 over pi. And that one is corresponding actually to a rectangle where the ratio of the square of the sides is irrational. And there's been some work in this there's been some work to try to improve the constant in Plejel's result in recent years due to Bourgain, Donnelly, and Steinerberger, where they all essentially use improvements on Faber-Kahn. But as you can see, between our 0.69 and 0.637, there's still quite a way to go. And a step in the right direction is actually the hexagonal conjecture, which is coming from the area I mentioned earlier, the spectral minimal K partitions. There, the conjecture is that if you let K go to infinity, the optimal partition should be the hexagonal one. And if it was shown to be the case, then for Plejel's theorem, we'd have an improvement of the constant to 0.677 rather than 0.69. So that's a very interesting open problem to show the Polterowicz conjecture, and also along the way to improve the Pleijel constant would also be good. So let me come back now to my main question, which is how many nodal domains there are. So we have from Plejel's theorem that there's finitely many Dirichlet Courant-sharp eigenvalues, and in the case of Neumann, Pleijel in this pioneering paper from '56, he also showed that the square has finitely many Courant-sharp Neumann eigenvalues. And then in the paper I just mentioned from Josef Polterowicz, he showed that in 2 dimensions with his analytic boundary, all are finitely many Courant-sharp Neumann eigenvalues, where the Pleijel constant is the same gamma 2 as before. And then more recently, Courant and Lena, he obtained a result in higher dimensions and showed that for Euclidean domains in Rn with C11 boundary, they have finitely many Courant-sharp Neumann eigenvalues with the same gamma n, and also Robin eigenvalues when H is non-negative. And the C11 here we can think of as the rolling ball condition, that you would be able to roll a ball all around the boundary. So, so for the case H negative, to the best of my knowledge, there isn't at present a general result. And later I hope to tell you something about, at least about the square for H negative. But for now, what we know is that in the case of Dirichlet, there are finitely many Courant-sharp eigenvalues, and for Neumann and Robin with some regularity of the boundary. So far, it's known in these cases, but we would hope with less regularity, it's still the same is true. So now that I know there's finitely many, there's then 2 questions that maybe come to mind immediately. One of them is how many are there for my given, if you give me a domain omega, how many are there? And the other one maybe is how large can they be if you give me a domain omega? So let's suppose you give me some domain omega in Euclidean space, finite measure. Then with Mikhail Vandenberg, we obtained the following bounds. So we have, if I define mu omega epsilon to be the volume of an interior tubular neighborhood of the boundary of width epsilon, and then I take this epsilon omega, it's the smallest epsilon, so that this volume is not too small. Then we have bounds in the following form. So I have a set in Rn, they depend on n and then on this epsilon omega. And C, math frac C omega, it's the number of Courant-sharp Dirichlet eigenvalues of omega. It's bounded by a constant depending only on n, the volume of omega on epsilon omega to the n. So what you can see is if I have, let's say I fix the volume of omega to be 1 and I have a very long thin domain, then this quantity epsilon omega will be very small. So then the bound will be very big. But in the case where we have, for example, a very long thin rectangle, we come back into the case of Sturm where all of the eigenfunctions are Courant-sharp if I take sufficiently long and thin. So we can get as many Courant-sharp eigenvalues as we like by taking a longer and thinner rectangle. So in some ways, this is the best we cope. Obviously, with such a generality, you could expect this to be quite crude. And since I'm here talking about bounds, I'd like to mention as well that there have also been bounds obtained by Erard and Helffer for planar domains with a regular boundary, which involve the cut distance to the boundary and the curvatures of the boundary as well as the length. And in the case of Neumann with Courant and Lena, we also obtained bounds for domains with C2 boundary. And in the convex case, it was quite explicit, depending on the rolling radius and the volume of the domain and the perimeter. Okay. So looking at this bound, as I said, it might look quite crude. So let's see what it looks like on a particular domain. And since the square is the one I'm interested in, let's see what it looks like for the square. So in the case of the square, the bound for C is 710,881. But actually, it's been known due to, well, in Pleijl's original paper and then some gaps filled by Erard and Helffer, there's actually only 3. So this bound is rather crude, as you can see, because there's really only just 3 of these Courant-sharp Dirichlet eigenvalues for the square. So we did pay quite a big price to have such a general domain up there. Of course, we're also paying to use the Faber-Cahn inequality in this case as well. And so how many Courant-sharp eigenvalues are there? Well, we say for the square there's 3. There's also been computations for the disk with Dirichlet, balls, the cube, tori, triangles, and very recently the Mobius strip as well. In the case of Neumann, there's been computations for the disk and for balls. And for the square, the situation of Neumann is like this, that there are 5 Courant-sharp Neumann eigenvalues, the first and second as usual, and then the 4th, 5th, and 9th. And this was really where our investigation started with Erard-Helffer, because we were looking at these 2 results and we wanted to know what happened to the 4th, 5th, and 9th for the Neumann case. Because if you remember, in the very beginning of the talk, we said that the Robin eigenvalues, they interpolate when H is positive between Neumann and Dirichlet. And so what we wanted to do is try to understand what happens to these particular cases, the 4th, 5th, and 9th, as H varies, the Robin parameter varies. So whether or not it's possible to follow the Courant-sharp Robin eigenvalues from the Neumann case, H is 0, to H is plus infinity. So this was where our investigation started. And on the next slide, I'm going to just remind you what the eigenfunctions and eigenvalues look like for the Robin problem on the square. In the case of positive H, I'm going to talk about positive H for the next section. And you'll see that the benefit, of course, we know the benefit of the square is that we have these explicit formulae available, but hopefully you'll see from some of the arguments that they don't only apply to the square. Okay, so here's just a quick reminder. We can write a basis of eigenfunctions, of course, as products of the eigenfunctions on the interval, and they look like the Dirichlet-Neumann cases, so I have products of cosines and sines. But I also have this parameter alpha p, which is coming from the Robin boundary condition here. and alpha p, it's the unique solution in each interval p pi, p plus 1 pi to the Robin boundary condition. And then the corresponding eigenvalues, rather than like in the Dirichlet case that they're sums of squares of integers, they're sums of squares of these alphas divided by pi squared. So we'll have to be careful with the dependence on h, as we would expect. Okay, so we're interested in which of the Robin eigenvalues of the square are Courant-sharp when h is positive. And we know already, and so to determine that, I should make some remarks. So the first one is that if my kth eigenvalue is Courant-sharp, then lambda k is larger than lambda k minus 1. That otherwise I would contradict Courant's theorem. And then now my objective is to find which eigenvalues are Courant-sharp. So if I want to show that the kth eigenvalue is Courant-sharp, then I'm going to have to find an eigenfunction in the eigenspace with exactly k nodal domains. And if I want to show that the eigenvalue is not Courant-sharp, then I'll have to show that every possible combination in the eigenspace doesn't have k nodal domains. So if I have multiplicities, then I'm going to have a lot of combinations to check here. And maybe one important thing to say at this point is that in the case where there are multiplicities, the number of nodal domains isn't fixed. So it's not that in one eigenspace, it's always the same number of nodal domains, and then for another eigenvalue, it's different. Even within the eigenspace corresponding to lambda k, the number of nodal domains can change depending on which linear combination of eigenfunctions we consider. Okay, which ones are Courant-sharp? So we knew, of course, that the first and second are Courant-sharp for h positive. The third one isn't, because it's equal to the second one, and as we said, to be Courant-sharp, it has to be larger than the lower one in the sequence. And the fourth one, it corresponds always to the pair 1, 1 for any h, and so it is Courant-sharp because we have the nodal lines x is 0, y is 0, giving us a splitting into 4 squares. So we can say something about the first 4 eigenvalues for all h positive. But of course, the situation becomes more complicated as we move to higher eigenvalues, because we'll have many crossings potentially between the different eigencurves depending on the value of h. And one of the cases that we were interested in, if you remember from the Neumann problem, in the Neumann case, we had that mu9 is Courant-sharp, but lambda 9, the Dirichlet eigenvalue, is not Courant-sharp. So this was one of our cases of interest. And in that case, we could show that there is some value of h, so that the eigenvalue is Courant-sharp up to that value. But afterwards, it's no longer Courant-sharp. And if I just show you here, I have the first 13 eigenvalues given as functions of h. And the ninth one, it starts off that for h is 0, it corresponds to the pair 2, 2 in these alpha mn notation. And 2, 2 is the one which gives me 9 subsquares. There's 2 vertical 0 lines and 2 horizontal ones. But then at some point, 2, 2 takes over the pair corresponding to 0, 3. And at that point, when it becomes 0, 3, we can use symmetry arguments because we have these explicit formulae available. They're trigonometric functions. We can look at the symmetries and show that actually for 0, 3, the corresponding, the number of nodal domains must be even. And since it's for the 9th eigenvalue, it's not Courant-sharp. But you can imagine as we consider higher and higher k, there could be more complicated situations and more crossings as we go. So the situation is quite delicate, dependent on h. Okay, so that deals at least with the case k is 9 for h positive, but we were still interested in k equals 5, and actually it would just be great if we could say something about in general what k's can be Courant-sharp. So you remember the Pleijel argument that we looked at earlier, where we applied Faber-Clan to all of the nodal domains. In the case of the Robin problem, we can do a similar Pleijel argument, and when we did that, it's also similar to Helffer-Persson-Sundqvist for Neumann. And when we do that, what we have is that if my eigenvalue, Robin eigenvalue on the square, is Courant-sharp, then k is at most 519. So that would mean that to say something about the Courant-sharp eigenvalues for any h, I would need to check 519 cases, or maybe 515, since I know the first, second, third, fourth, ninth, so 514. So in any case, still a lot of cases to check here. And if you remember back to the Pleijel result that we mentioned earlier, for the square there's only 3, and when Pleijel does this kind of reduction, it brings k down to at most 34. And even for Helffer-Persson-Sundqvist, when they do in the Neumann case this reduction for the square, brings k down to 208. So here we still have a great deal more than what was even in the Neumann case. So at this point we said, okay, this is okay, but we didn't take h into account at all. So if we do take h into account, can we say something better? Can we reduce the number of cases lower than 519? So the idea was, to which extent can the results from the Dirichlet case extend to the Robin case if I stay in the regime where h is large? And one thing that I should say is that this theorem, it did allow us at least to do a kind of bootstrap to show that the nodal domain, the volume of the nodal domain, can't be too small, which is related to the problem I mentioned earlier with the scaling of the Robin parameter when you rescale the domain. So that did help us out with that, and it did allow us to consider large h. But I wanted to talk to you about another approach for the large h case, which actually is to do with perturbations, and it's going to be based on this theorem due to Nodal here. So remember, we're interested in Courant-sharp Robin eigenvalues of the square for large h, and so we'll always have as a reference what the nodal partition is for the Dirichlet eigenfunction for the same lambda k. And so the idea is that by this result of Nodal, the number of nodal domains, it can only change if either the number of interior critical zeros changes, or if the number of boundary zeros changes. And by number here, I count how many there are and also the order of vanishing. So what we're gonna do in the next part of the discussion is start from the nodal partition for UK corresponding to Dirichlet lambda k, and then we're going to do a small perturbation of h and try to understand what happens to the nodal partition and whether there are changes in the number of interior critical zeros. So the result that we have with erard-Helffer is the following, and maybe I'll start halfway down here. So I have a smooth family of eigenfunctions for the Robin Laplacian. They're associated to some bounded eigenvalue. And then what we could show is that there is some epsilon 0, so that no nodal domain of any of the eigenfunctions in that smooth family has smaller area than epsilon 0. And so what the idea is I start from the nodal partition for the Dirichlet eigenfunction corresponding to this eigenvalue, and let's say it starts off that, and it has an interior critical zero. So here I have in blue what would be my nodal set. I look locally and I take a small disk around this interior critical zero, and I take the disk small enough so that let's say its area is epsilon 0, and then I do the smooth perturbation of h. So I move through the family and I try to understand what happens to inside this disk to the nodal set. So either it's going to stay like this and I don't lose any critical points. Maybe I lose a critical point, but one thing which can't happen is I can't suddenly create several loops inside this disk, because if I did, they'd have smaller area than epsilon 0, and that wasn't allowed by this proposition. So the only thing that's the only options for the changes to the nodal set is either it stays unchanged or I lose a critical point. And if you look here on the left, then this is either going to be 4 global nodal domains or 3. And here it's going to be either 3 global nodal domains or 2. And so under the perturbation, the number of nodal domains might decrease, but it won't increase because I can't suddenly create loops inside here. So what we know so far is if I start from Dirichlet and do this small perturbation, I can't increase the number of nodal domains. So if my Dirichlet eigenvalue already didn't have an eigenfunction with k nodal domains, then after the perturbation it won't have gained any more, so it's still not Courant-sharp. So what we could obtain in that way was that for h large enough, there is some h1, so that h larger than that h1, the Courant-sharp cases for the Robin problem, they're the same as Dirichlet, only the first, second, and the fourth. And I should mention that that proposition to do with perturbations, the proof of it's based on the Robin-Faber-Kahn inequality, so we really use there that we are in the case h is positive, that the minimizer of lambda 1 in the Robin case with h positive is the disk. Okay. So that's what the situation looks like for large h. Oh, and also we did have to analyze the boundary points close to the boundary as well, because of course there we have the mixed Robin-Dirichlet condition, and there was a similar perturbation argument there too. And I should also say that the regularity required on the domain wasn't only for the square that we have this, we could have p squared c as well for the boundary as well. All right, so that tells us something for the large h case. So let me say something now about the small h. So if you remember, h0 was Neumann, and there we had 5 Courant-sharp eigenvalues. And now we're interested in the extent to which it's possible to extend the Neumann results to the Robin case when h is small. And the result that we have is the following. So in the small h regime, there is some h0, so that for h smaller than that h0, Courant-sharp cases for the Robin problem, they're the same, except for the 5th one as the Neumann. So the 1st, 2nd, 4th, and 9th are Courant-sharp, but the 5th one isn't for small h. And to obtain this, we did follow a similar strategy to the Neumann case of Helffer-Persson-Sundqvist. So we tried to eliminate the number of cases by a Pleijel argument, then further eliminate by using symmetry properties. And then we were left to try and obtain a perturbation type argument like the one I just described, except the problem there is that we start from the nodal partition for Neumann eigenfunction. So we can't use the Robin-Faber-Kahn inequality, so it was a little bit more tricky to set up. But there is a perturbation argument available there as well, and we had to check through the remaining list of cases. But the important thing is that for small h, the 1st, 2nd, 4th, and 9th are Courant-sharp, but the 5th one isn't. And I can just show you what happens. So here is some of the possible nodal partitions for the 5th Neumann eigenfunction of the square. They're corresponding always to the pairs 0, 2, 2, 0. So we take a linear combination of those. And for different values of theta, so theta is 0, and then I change theta. Theta is pi over 4. I get exactly 5 nodal domains. And then I increase theta. And you see that the number of nodal domains, it changes from 3 to 5 to 3 to 4 and then to 3 again. But this is all in the same eigenspace, that there is this change of the number of nodal domains. But what happens for the Robin case, even for small h, Well, then we have something that looks like this. So for h is 0.01, the boundary points meet on the vertical edges before the other sides have had a chance to intersect the boundary, and then we lose them here and here before the others have reached the boundary, and then when those ones reach the boundary, these ones have already left. So actually we have 3, then 2, then 3, then 4, then 3 nodal domains, but never 5. And so for h small, there is, if you like, a kind of symmetry breaking, because you can see from Neumann here, everything is nice and symmetric. You could cut this one here and fold it over and fold it and fold it. But for Robin, we kind of lose some of the symmetry because we couldn't just, they don't meet the boundary at the same time as these ones here. Okay, right, so this was for the small h regime. And that's what I wanted to say about the positive h case. So let me talk a little bit now about our most recent results, which are on the h negative case. So before I do that, I need to remind you possibly of what the eigenvalues and eigenfunctions look like in the Robin case on the interval, because we're then going to take, of course, products of the eigenfunctions. So for the interval minus pi on 2, pi on 2, I have always one negative Robin eigenvalue, and for certain values of h, there'll even be 2. So if h is smaller than minus 2 over pi, there's 2 negative Robin eigenvalues, and then the other ones, they're approaching Dirichlet eigenvalues from above. And the corresponding eigenfunctions look similar to before, except for the negative ones, we have hyperbolic cosine and hyperbolic sine instead. So in the notation that I'm going to use, the alphas will be as before, corresponding to the Robin condition, except now they're in the interval pi minus 1, p minus 1 pi, p pi. And then the betas will be corresponding to the negative Robin eigenvalues. So one important thing to say about these betas, which you probably already thought about here on the first slide, is that they're exponentially close. So as h tends to minus infinity, the beta 0 and beta 1, they're exponentially close, and the beta 0 is bigger than the beta 1 for h negative. So what do our eigenvalues look like now on the square? So when I'm in the case where h is larger than minus 2 over pi, either I have the sum of 2 beta zeros, or those given by beta 0 with an alpha q, or those given alpha p and alpha q. And then when h is less or equal than minus 2 over pi, I have either the 2 betas, or a beta with an alpha, or 2 alphas. So what you'll see is that the ones given by 2 betas are always negative, the ones given by 2 alphas are always positive, but then for these ones here in the middle that are given by 1 alpha and 1 beta, they'll be negative for a certain value of h. So for h negative sufficiently large in absolute value, these ones are going to be negative. And also they're going to have multiplicity 2 in that case. Whereas if you think about if this one here in the middle isn't negative, maybe it's going to cut across these ones given by the 2 alphas and we'll have higher multiplicity. So you can see here in this figure, any of the eigenvalues that are given by a 0 and a q, or a 1 and a q, they're going to tend to minus infinity. The ones coming from the alphas are always positive, but the ones given with 0q, 1q are going to cut across some of the positive ones, and then we're going to have higher multiplicities, higher than 2 at least multiplicities there. All right, so if you look here, the 9th one is again given by this red curve, which is corresponding to 2, 2, and then it gets cut. It intersects with the green one, which is 0, 3. So this is now again like the positive h case. And what we're able to show, so again, the first 2 are Courant-sharp for any h negative. The 3rd one isn't because it's equal to the 2nd. The 4th one is it corresponds to 1, 1. And now for the 9th one, we have the same kind of behavior as in the positive H case, where there is a critical value of H9, so that the 9th one's current sharp up to that value, but then afterwards it's not current sharp anymore. But if you remember from the positive H discussion, one of the interesting cases was actually the 5th one. And the 5th one, because it was current sharp for Neumann at H0, but then for small h it wasn't current sharp anymore, we kind of lost the crossings with the boundary. And here in the case when h is negative, it is always current sharp. And there is, we can even say one of the eigenfunctions is always current sharp. So for the 5th one corresponds to the pair 0, 2. And this eigenfunction, this linear combination from the eigenspace is Courant-sharp. Here in these figures, I have some of the other linear combinations, but the one which corresponds to this eigenfunction is the red one here. So you see that there's 5 nodal domains there. So on the left here, it's for h negative close to 0. I think this one's h close to -2/pi, and this one's h is -2. What you can see is that there's one here with 5 nodal domains, but here there's actually the red one and the purple one have 5, and then here there's a lot more options. So that is interesting. But I wanted to show you this because I think you can see from this what would be a strategy of the proof. What we did was to show that the x-axis and the y-axis are not in the nodal set. And then on each side, this eigenfunction is going to have to intersect the boundary exactly twice. And so the only way it can do that without crossing, to preserve the symmetries without crossing the x and y axes, is to join up on the adjacent side there. And that one gives us then 5 nodal domains. So that deals with the cases 1, 2, 3, 4, 5, and 9, but what we'd really like to do is say something about the higher k, so k at least 6. And so then we wonder what can we say about these higher cases. And the perturbation argument that we described earlier for the Dirichlet, or close to Dirichlet case, as I said, was depending on the Robin-Fabre-Khan inequality, which doesn't hold when h is negative. And for h negative and absolute value sufficiently small, it was shown by Freitasch and Krejcirek that the disk is the maximizer, not the minimizer. So the ideas for the perturbation are more tricky here. Even from our Neumann case, we had to impose conditions to get a kind of perturbation. But the bigger problem in some sense is that when h is negative, as we mentioned, the multiplicities could be larger than 2. And the figures that I've shown you so far, even here, they're linear combinations of 2 eigenfunctions. So we know how to analyze those. But if I look here, I would have a multiplicity 3, for example. So that we don't know how to deal with the larger multiplicities. So what we'd like to do is be in a situation where there's multiplicity 2. And there is a situation available where that holds, because we have the negative eigenvalues corresponding either to 0q or 1q. Each one of those is going to have multiplicity exactly 2. And so we would be able to analyze the nodal sets using the techniques that we have, the Euler formula and Sturm's theorem. And in addition to that, there was an extra incentive for the negative case, because in that case the nodal set can't have an immersed circle that doesn't intersect the boundary, because if it did, then that would have to be a Dirichlet corresponding to a Dirichlet eigenvalue. We'd have an immersed circle, 0 on the boundary, eigenfunction not changing inside, but then Dirichlet eigenvalues are positive. So we also know that the nodal set is connected to the boundary in that case. And so the benefit of restricting to this negative case corresponding to those pairs was that we could do the analysis of the possible topologies. And what we can say is, in the case where k is at least 6, there is some critical H star, so that the negative Robin eigenvalues, they're not Courant-sharp. So the eigenvalues corresponding to these pairs, well, a pair of this form or this form, and when the eigenvalue is negative, it's not Courant-sharp. So that means if I go for H negative sufficiently large in absolute value, I know that the eigenvalue is not Courant-sharp. So just to kind of finish, I'll come back to Pleijel's theorem in this setting, because using counting arguments, we could show that for the H negative case, the number of positive Courant-sharp Robin eigenvalues of the square is less than, well, it's bounded uniformly independently of H. There is some constant independent of H which bounds it. And using the properties of the Robin counting function, we could then say there is another constant which is also independent of H, so that the number of Courant-sharp Robin eigenvalues is less than this constant. And you can see that if my H here under consideration was smaller than the H star that I just mentioned for the 0q, 1q case, then the n tilde is just going to be the n number of positive plus 4. So we do have a Pleijel theorem for the square when H is negative. And that's what we could get out of the result I just mentioned. And so just for the last slide, there are still, of course, questions. So we talked about the case when H is very large, when H is close to 0, and then when H is negative, large absolute value. So there's also the intermediate cases to think about. Also, what about other domains? But you saw that many of the parts depended on the explicit formulae for the eigenfunctions and eigenvalues. And then in general, whether there's a Pleijel theorem when H is negative. And of course, one of the big open questions, what's the optimal Pleijel constant? So yeah, thank you very much for your attention.
Thank you. Are there any questions?
Jonathan, Mayor, I'm just wondering, does anything interesting happens for disks?
I don't know. I think it would be interesting to know that. So for the disk, the Neumann case, there are only 2, the first 2, and then for the Dirichlet case, there are also only 2. So it would be interesting if something happens in between the Neumann and Dirichlet, whether some Courant-sharp eigenvalue, where the one eigenvalue could become Courant-sharp for some H, that would be interesting. But I don't know the answer yet.
You get nasty special functions on one hand. On the other hand,
yeah,
there is less chance of higher multiplicity, which might help as well.
So,
may I ask you a question also? It's Ari. I have maybe a bit stupid question. So if you have a square, and then you consider H complex, so the operator is not self-adjoint, but the eigenfunctions and eigenvalues, I suppose, would be easily extended by analyticity. So could you say something about that? About nodal domains and about well, what happens with the eigenvalues and the nodal domains.
Yeah, I haven't tried to do that, but I think there are some works on at least the complex case for some of the domains by Sabine Vogler and James Kennedy. I think they had quite recent work looking at the Robin case with H negative. I think it was from last year actually. But yeah, I think it's possible.
Okay.
I forgot one of the authors. It's also Robin Lang. There were 3 authors, Lang, Bergley, and Kennedy. Thank you.
So can you say anything about, let's say, triangular domains by starting with squares and then say bisecting them with a diagonal? And if you can say something about triangles, can you then say anything about domains that can be tiled with triangles?
That's a really good question. I haven't tried to do that, so I don't know, but it would certainly be interesting to look at that. I think some of the results that are done for some of the other domains, you do use those kind of ideas, like some of the tori, for example, if I remember correctly. So yeah, maybe that would be well worth looking at.
Yeah,
The
I
trouble
guess
with the triangles for Robin is with the formulae. Yeah, I think I'm not sure if the closed formulae are known or if they're sufficiently explicit to, in the Robin case, to be able to get hold of the same kind of information as we have for the square.
Well, you probably need a lot of symmetries.
Mm-hmm. Yeah.
But for Robin, I'm not certain you can even do it for arbitrary h for 60, 30, 90 or 90, 45, 45 for Robin.
Yeah.
My impression that you can, it would be too good to be true.
Any other questions or comments? Okay, if not, then let's thank Katie again for a very nice talk.
Thank you.
Thanks. Bye.